Hi everyone, welcome back to Line. Today let's see together how to perform a registration between medical images, one of a CT and the second one of an MRI of the same patient using SimpleITK package. So I got this Jupyter notebook from the original repo of the ITK, of the SimpleITK. You can find by yourself. You can install it using this thing, git clone github.com simpleitk/tutorial.git, and this will clone that in your environment. Then you can install IPYMPL just for visualization in the new Jupyter, and the main important is to pip install SimpleITK. Then when it's done on your side, you can go ahead with the code. My goal in this video is to explain step by step the registration. So again, what is the goal of the registration? Even in volume, even when we perform a registration between volumes of medical imaging, and the same thing when we perform a registration between two 3D point clouds. The goal is to get a transformation matrix, which is 4x4 matrix, and contain a 3x3 matrix, which is a rotation part, so 9 elements, and the translation part, about 3 elements. Okay, so we need to find them. We can also explain the rotation matrix by the Euler angles, so we just need 3 elements of the Euler angle: pitch, row, yaw, and roll. So let's go ahead with the fixed image and the moving image. We need first to choose our two inputs. So we need two images from the volume, two volumes, so one from the CT, one from the MRI. These two inputs are part of the training data from the retrospective image recognition registration evaluation project. So it's very important to choose here float 32 and not for example 16 or 8, because we need to be really precise in order to find the parameters of the registration. Then we need to choose the CT window level and MR window level. What is that exactly? So the window level, this format, so I added this comment just to understand that the window here and the level. So we need first to choose the level, and then the window, it's like plus minus window divided by 2. Meaning when we see an MRI or a CT image, we see the gray scale, we see the value of the gray. So we just need to specify. It completely depends of the tissue visualization. If we see a brain, if we are interested to see another part, so we can choose different window and different level, because the scale, the value of the gray will determine and will define the part that you will be able to see. If we choose for the CT here between minus 255 to 579, so we will be able to see exactly this. Okay, we're going to see that in a few minutes. And the second one will be in fact between 2 to about 1000, okay, for the same brain visualization. So I remind that it's the same patient, one from the CT, the fixed image here, and the second one from the MRI, the moving image. So when we choose in fact these two window and level, these are default parameters from the original repo. So we can be based on that. So we need now to use the GUI function, the GUI function of the SimpleITK package. So then let's go ahead and let's see. So I can also do that together. So we can see that now we can do that. And if I want to click here and to get, for example, here, I don't have any answer. Okay, I cannot click on the image. It's only a visualization step. I can also move the image slice. What we see here, in fact, just need to imagine. When we have, in fact, the image in 3D, we just take like a slice in the Z axis, and the slices is exactly here. So it's only different part of the brain that we can see. And if we take, for example, the middle, and in the image slide also the middle, it will be maybe close to the same part, but it will not be exactly the same. Why? Because it's already not registered. So let's continue. Now, to perform a classic registration, we need first to get the initial transformation. To get the initial transformation, we are going to use Euler 3D transform and the very important thing, dot geometry. So the transform initializer filter dot geometry, meaning that the registration will be performed not between values of pixels, but between the geometry from the CT to the MRI. So you can see here that if I'm going to run that, the center, so currently what we have done, it's only to get a translation, okay? As you can see, the rotation matrix is about identity matrix, so without any transformation. But what we did for the initial transformation, we just took the center of the CT and the center of the MRI, and we did a subtraction, and then we got the translation. So we can see here the center, the final center, and the translation that we need to perform to the moving image in order to be translated on the same center part, on the same centroid of the fixed image. Then we have, in fact, this GUI. So we can see now this kind of registration, but again, we haven't performed yet a registration. What we have did now, we just translated the moving image to the fixed image to the same centroid, to the same center of world. But now, if I'm trying now to use these parameters in order to get this part on the same, I just need to click here, and you see that it's not exactly the same. What I expect to see here, I expect to see the exact geometry of that, but because now I haven't still performed the registration, so it's completely acceptable to don't have this thing. So we need to go ahead with the code and then to get the correct parameters. So just to summarize, we got now only the translation parameters from just basic subtraction between the centroid of the two volumes, and now we are going to get the true registration. So according to the original repo, they advised us to use three runs. So the first one is without, in fact, the scaling parameter, which is here. Sorry, it's already commented. So let's see line by line. So we need first to create the registration framework, so registration method. Then to add the metric. What will be the metric? It will be, in fact, the Mates mutual information, meaning the mutual information between the CT and the MR image. Then the sampling strategy, what does it mean? We need to choose a sampling because we cannot use all the voxels. Let's take, for example, the CT. Let's imagine the CT has, in fact, 500 let's say the volume image has about 26 millions of voxels. We cannot perform a train algorithm or even estimate a gradient descent using 26 million of parameters. It's not possible. So we need to use a sampling method. In fact, here we can choose 1%, and then with that we can say, okay, we have about 260 thousands of voxels used to compute the registration, so it's acceptable. Okay, let's go ahead. Then we just choose the interpolator, so it will be linear in this case. Use the linear interpolator to estimate intensity values, add non-grid position during transformation. Then the gradient descent, so as exactly in deep learning, we choose also a learning rate, a number of iterations, convergent minimum value, and convergent window size. You can read the comments. And that's it for now. Okay? So then it's only about some details, and then we can execute this line, the most important one, in order to execute the registration between the fixed image and the moving image, and we got the final transform containing the rotation and the translation. So let's run that. and okay, 4 seconds to see in fact this curve. And now, so you can see the final transform. In the final transform, I have my matrix of rotation, I have the offset of translation, and I can now test the registration. How can I test? I just need to move the slice of the moving image, for example, in this part, and to click, and I expect to see the exact geometry when I click here. So I don't see the exact geometry, meaning that the registration is not well performed. I can try another part. It's not a good result. So let's now trying to optimize that. First thing we can do is to uncomment this thing. Why? Because it will automatically scale optimizer parameters. The rotation in radians and translation in millimeter have comparable physical impact. Currently, it was a translation that has a better impact, okay, a most impact. So let's try with this parameter after uncommented here. Okay, so we have about so 22 seconds to get the optimized part after uncomment these params. Let's now get the final transform. This is the values. And now let's test the registration. Let's try. Okay, we can see that it's better. We can see that, for example, here, if I click, I have something that is pretty good. Okay, it's closer, but it's still not perfect. Okay, okay, it's really closer, but it's still not perfect. Now we are going to uncomment this part. Or in fact the multi-resolution setting. So we define image peer image shrinks factor, level 1 image reduced by factor 4, level 2 image reduced by factor 2, and level 3 is a full resolution fine alignment. We also apply a Gaussian smoothing at each level to reduce noise and improve robustness, and we specify that smoothing sigma values are in physical unit, not in pixels. So let's try running that. So about 14 seconds to get this graph, okay, the optimized registration. Okay, on your side you can also compare the result for each simulation. And now let's try, okay, so here, okay, so I can see now that it's very pretty good, meaning that I have the same kind of part, okay, I remind that it's the same patient. This is the CT, this is the MRI. When I move the MRI in another part of the brain and I click on this part, I can find in fact the same part in the CT, meaning that the parameters of the rigid registration seems to be pretty good, okay, after go through this optimizing process. That's it for this video. I hope this was clear for you. Let's go ahead next week with other and more advanced registration for medical images. Thank you.